Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with a geometry video for you all. And today's video is all about transformations in geometry, and I will get into what that means and exactly what we're going to be doing with transformations. And before we get into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our channel's latest posts at eCoreAcademy. It's all very greatly appreciated if you do all three of those things. And also, please make sure to share these videos as well. So yeah, like I said before, today's geometry topic is all about transformations, and this is our part one because I will be continuing this into multiple segments since it's a very large lesson. So this is our first part of transformations in geometry, and the whole theme and purpose of today's lesson is to discover what geometric transformations are and how exactly they're performed. So I'm sure many of you have heard of the term and the word root transformation. Transformation is some sort of change that occurs. If you haven't heard of the movie Transformers, where they turn from vehicles into actual active robots. So they're changing their whole entire their look and their appeal and their aesthetic appeal. However, they're not necessarily altering what's physically given to them. That means their materialistic objects are not altering. So that means in transformations, what happens is you're given a certain material object, and you're taking that material object and you're actually devising some sort of action plan with certain given transformations in order to develop some sort of new image, something that's going to be as a result of some process that you did to make something else, something new. So if you're given a real life example, say for example, you're given a little ball of clay. Clay is something that is a very meshable, it's like Play-Doh. It's a professional Play-Doh. And if you're given a ball of clay and you're trying to perform some sort of transformation from it, you're still taking that material, but what you can do is you can stretch it out, or you can ball it up into an even smaller and more condensed ball, and that's somehow changing the aesthetic appeal of it. All right, let's jump right into geometric transformations. So before we get into what exactly transformations are, we're going to first look at shape relativity, because shape relativity plays a very important role in transformations in mapping your pre-image to your image, and I'll explain that right here. So basic relationships between shapes, that's what this slide's all about. So like I said before in my previous video about measuring angles and measuring length, there's something called similar shapes or similar figures. And these are shapes that have the same size, that do not have the same size, but have the same shape. So say, for example, if I were to show you a triangle, draw a little triangle right here, and I can label this triangle A. And basically what happens is I can draw yet another triangle here, and I can label that triangle B. And what I can say is triangle A and triangle B are both similar to each other, and the similarity sign is this little swiggle right here. That's how you express similar figures. And so I'm going to say triangle A is similar to triangle B. That doesn't necessarily mean that they're the same size, as you can obviously see here with the naked eye, that they aren't the same size. However, they do have the same shape, equilateral triangle, a specific type of triangle. And since they have the same angle measures and the same exact shape, but not the same size, they are said to be similar. And of course, they don't have the same location as well, position and mapping, and their position and location on any 2D plane. Next, we have our congruent shapes, which I've also mentioned before. It's very similar to a similar shape, except it has a bit more of a qualification standard. Congruent shape has both the same shape and size. So unlike similar shapes just having the same exact shape, it also has the very same size. But keep in mind, neither similar shapes nor congruent shapes, neither one of those two classifications of shapes have the same exact location. So if I were to redraw a new triangle A and a new triangle B, so I'll make this A and another triangle B, and say for example we already know that A is congruent to B. And the way to write that congruent statement is this. It's taking this little swiggle and putting it on top of an equal sign. That's how you write congruency. So that's how you say congruent. So triangle A is congruent to triangle B. And once you've made that clear, you can basically see here A is approximately equivalent to B. And since they're both equivalent, those are said to be congruent shapes, and they have the same exact size, but they do not have the same exact position, which makes them congruent shapes. And finally, we're going to, after looking at similar shapes, congruent shapes, we see this little relativity concept that we've come across, and now we can actually look at what transformations are, which is the whole topic of today's lesson. And so a transformation, on its own, its basic geometric definition, is a one-to-one mapping between two sets of points. So all that is basically what happens is you're taking a single point here. So you're taking a single point of a triangle. So I'll name this triangle C. And all you're doing is you're moving a single point the same. So say, for example, let's take this top point here. I'm going to break this down for you all. So if you take this little top vertex of triangle C as shown here, right here, if you take this vertex right here that I'm circling around, and you're moving it, say, for example, 5 units. 5 units. I'll say that 5 units across, and you're mapping that right here. That means every single other vertex of the triangle must also be moved to 5 units. And that what that does is it maintains similarity and not necessarily maintaining your congruency. However, and I'll explain that later on, but all you're doing is you're moving a shape, and each one of its vertices is being moved the same distance as the other. And what that does is, in essence, it maintains the same triangle, the same shape of a triangle, and makes two similar triangles. So that means this triangle right here is similar to this triangle over here. So that's what transformations do. It basically maintains similarity, but not always congruency. And we'll get into what types of transformations maintain similarity and what types of transformations also maintain congruency. So this is our part 2 of shape relativity. And I'm just going to be throwing a couple more definitions that you need to know and get familiar with before we get into the actual process of transformations and what these different types of transformations look like. So more basic relationships between shapes. So first basic definition that we have here is the pre-image. So like I said before, a transformation is a one-to-one mapping. You're taking one figure and you're basically transforming it and moving it to a different location, forming an entirely new figure. Now, there's that in that process, there's two figures that you're looking at, your pre-image and your image. So your pre-image is the original figure before a transformation, and basically that's any figure. Say, for example, let's do the triangle example again. And if you take this triangle here, this is your pre-image. But then when it comes to the image is basically what takes the pre-image, undergoes the transformation, and turns into the image, which is the figure after transformation. So say, for example, this is an image. It's any figure given on a plane. And what happens, the pre-image actually is used to develop the image. So this is the pre-image right here. And the pre-image is basically altered under some sort of transformation. Say, for example, we did a translation, which is basically a movement, and I'll explain that later. And say, for example, we somehow do some kind of transformation represented by this arrow, and we end up with, I'll just label this here, transformation. So you guys are not confused. Transformation. And that's the process of this whole that's a process of this process. It's the main kind of factory type part of this whole entire relationship. It's the process of this whole relationship. And then finally, you're given your image, which is some sort of altered, shape. It could be in a different location. It might be a bit bigger. But this is basically what's the original copy. The transformation changes this original copy in some manner, and you get your image, which is basically the output. So it's input, process, and then output. All right, let's move on to right, and before we move on to that, I'm sorry if this is a bit cut off, but the coordinates of an image are represented by the prime of the letters of the pre-image. So what that's basically saying is, if you're given this triangle here, and you're trying to map it to this other image, so this is your pre-image, and you're trying to map it to this image of a triangle here, image of this pre-image. And what happens in this process is, say, for example, you're given the letter A, naming this vertex right here. Now, what happens is, for that pre-image, in relationship to the image, the image will take the prime suit of that vertex. So what that basically means is if this point is A and this is the corresponding point on this transformation of an image, then this point will be A prime. This little comma is represented to say A prime. And that just shows correspondence of similar figures. Now let's move on to the types of transformations, which is really the meat of this lesson, and then we'll also touch on the topic of how to actually execute these different transformations that I'll be showing you right here. So this is a part one of types of transformations. So there are 5 main types of translations and transformations. So first, before we actually move into what translations and transformations are, we have to first think about isometry. So isometry is the basis of any transformation and of major transformations. So isometry is a specific type of transformation that results in a pre-image that is congruent to the image. So remember how I said when you're undergoing some sort of transformation for a figure, you can either have a similar figure as an image, or you can have a congruent figure as the image. So basically what isometry does is it takes one figure, say for example we have a triangle here, and what it does is it undergoes some kind of transformation which changes its position or shape, but in this case it'll only change the position of a figure to give another congruent triangle right here. So that it preserves the size of the pre-image, and all it does is it just changes the position. So isometry is a transformation that only changes the position of a figure. And moving on to our very first type of transformation, we have reflection. So reflection is an isometric transformation. Like I said here, it maintains congruency from the pre-image to the image. So it'll keep the shape congruent under reflection. So if a figure is put under reflection, it is an isometric transformation that flips a figure across a line or a line segment, which is basically saying that it creates a mirror image of the figure. So if you think about yourself looking into a mirror, and what happens is basically everything flips. Everything is flipped completely. So if this is the mirror, and you're on this side of the mirror, this side will be the complete opposite of what was given on the other side. So basically what happens here is, say for example, we're given a line right here. And say for example, this is a mirror or a line of symmetry. That's where the reflection is going to happen. So say for example, this is a mirror, and this is a line here. If you're going to reflect it, what happens is the line and every point of the line will be the same distance from this mirror here as its reflection. So the reflection is the same distance from this mirror as its original image. And as you can see here, it's a complete opposite. It's just a flip over of what a mirror would do. So it's just a reflection. You're flipping over a figure, but it maintains the same exact shape, and it maintains the same distance from wherever you're reflecting that figure from. Now we're going to move on to our second set of transformations. And first, what we have here, our second transformation, type of transformation, is a rotation. And a rotation, like a reflection, is an isometric transformation that turns a figure a certain number of degrees. Now, remember how I recapped last time? A degree or an angle rotation is when an object is rotated across a center point. And it's rotated a certain number of degrees, called the angle of rotation, the amount of degrees that it's rotated around a central point called the center of rotation. So what that basically looks like here is, say for example, we take a line, or let's do a line here. And we're saying that this is our line, and this little point that I'm going to put here is our center of rotation. Now, we know that our angle of rotation, let's say for example, our angle of rotation, I'll state it here, is 90 degrees. So what that does is and I'll be expanding off of this into different videos, how to actually do your rotations, translations, and your reflections, how to do that on a coordinate plane. But just to get the general concept, I'm just going to be doing it on a regular chalkboard like this. So if you're going to rotate a figure 90 degrees, it's 1/4 of the way of an entire circle. So if this is the center of rotation and this is your line, the new line after being rotated 90 degrees will be here, because you're basically just rotating it across this line. And if you measure that, it'll be 90 degrees. And then for our last isometric transformation, we have our translation. As just to recap, isometric transformations maintains congruency. And this translation is an isometric transformation that slides a figure in a path without rotation or reflection. So basically all it does is you take, say for example, a triangle, I love triangles. That's why I've been using them as our main examples here. And say, for example, you take this triangle and you're trying to translate it over some direction. So what you're basically doing is you're moving this figure across a line. And like I said before, translations move across equal distances between all of their points to give a new triangle that is just basically shifted. So all you're doing is moving a figure up, down, left, right, or diagonally without rotating or reflecting it. So it's every other possible type of isometric transformation that doesn't involve rotating or reflecting. So all you're doing is sliding a figure without rotating it or flipping it side to side. So it maintains congruency, and it also helps maintain some sort of correspondence and similarity. And before we get into our final type of transformation, we're going to look at rigid motions. And that's very important to know before we get into this last type of transformation. A rigid motion is a motion that preserves the size and the shape of a figure throughout the transformation. So remember how I said transformations helps represent similarity in objects, but not necessarily congruence? Well, a rigid motion is a specific type of transformation that maintains both size and shape. So unlike just maintaining similarity, it also maintains congruency. So it keeps an original figure congruent to its, keeps a pre-image always congruent to its image. And the one type of transformation that does not involve isometry or rigid motion, which is basically the same thing, is a dilation. And a dilation changes the size of a figure, but not the shape of the figure by either enlarging and shrinking it. So if you think about our other three or other main four types of transformations, our other main three types of transformations that we have included here. I will not include the fifth one here, but I will include it in this next video. I wanted to say 5 types of translations for this transformations for this whole entire slide topic, because I just want to put that out there. But there are 4 main transformations. And I will get into the 5th one, which is a very special case type of transformation in a later video, so I don't confuse you all. But I just wanted to put that out there. And so thinking about the dilation, it changes the size of a figure, but not the shape, unlike every other transformation that we've come across, like a translation, a rotation, or even a reflection. Those 3 actually change the position of a figure, but do not alter its size or its shape, but the dilation alters the size of the figure. So say, for example, we're given a triangle like this, and we have some sort of point of dilation. And after we do this transformation, which is represented by the arrow, you're given a larger or a smaller triangle, and that's some sort of dilation. But it keeps the same exact type of shape, which is, the same triangle with a similar amount, with the similar corresponding degree angles. And now we're going to look at properties of transformation. So this is more of like the process. I'm just going to be tuning into these different types of transformations and more of their active processes and and showing you actually how it's going to be calculated in real life. So let's focus on rotations first. So in order to describe how a rotation occurs, there's 2 main parts. It's your center of rotation and your angle of rotation. So the angle of rotation for a figure is the amount of degrees an object is turned. I'm just going to redraw my example here with a line being drawn over here. So I state that my angle of rotation is 90 degrees. And the angle of rotation can be proved to be 90 degrees if you measure the amount of distance that this line rotates to this line. And if you measure that with a protractor, you'll get 90 degrees, and that'll be the angle of rotation. And then the center of rotation for any rotation transformation is the only point that doesn't move during a figure rotation. So it's basically where a figure is rotated off of. So I'm going to draw a circle here, say, for example, and we're trying to rotate the circle 90 degrees. Then the circle ends up here. So in this transformation, as you can see, the only object that doesn't move is just the center of rotation, the center point. But the circle does move. And in any relationship, if you're even given coordinate plane and relationships with coordinates, you will see that a center does not move, but everything else, even every other coordinate that's not even involved with the shape, will also alter its position. And I will explain that in our next lesson. And finally, we're going to look at our translations and our reflections. And I will be doing a separate lesson on dilations because it's a whole different topic that has to do with similarities. So I'm only focusing on the processes for translations, reflections, and of course, rotations. So for translations, the process is represented through a translation vector, which shows the distance and direction in which each point of a shape must move under a translation. So basically what that's stating is, like I said, a figure is any figure that is slided, meaning keeping its same exact corresponding position, but just moving keeping its same vertice relationships, but just moving along a certain line. So, like I said, it's going to slide some across some sort of some certain amount of points, and that sliding direction is shown through a vector. And a vector will always show your distance. So say, for example, you're trying to translate a figure 5 units. So what you would do is you take every vertice of, say, for example, this triangle here, and you'd move it 5 units in that certain direction. So this little line here shows my vector here, and that's same for all parts of this triangle. All vertices of this triangle must be moved the same distance, and that's shown by a translation vector. And finally, for a rotation, I apologize. That's supposed to say reflection. So that's reflection. Don't want to get you guys confused. So reflection. So finally, for our reflection type of transformation, we have a line of reflection, which is a line or line segment about which a figure is reflected. So remember how I said we're going to have this little line here in my previous example, and I said that we're going to have this line here, which is our mirror, in which this segment here, which I'm going to label segment A, is going to be reflected across, just like a mirror would in the same exact relativity and property. So basically, this line is our line of reflection, and this is where this line A is going to be reflected across. So if we see how many units across line A is from this endpoint right here to this endpoint right here, and all relationship from the distance here, everything is just going to be the complete opposite distance on the other side to get the reflection. So this is line B, and it's a direct reflection, and we know that because we calculate the distance from the tips of each and every of the tips of both of the endpoints of line A, and we're basically just taking the opposite of that direction, of that distance. So say, for example, this is 5 units between the endpoint of A to the line of reflection. Well, that means that the endpoint of line B to the line of reflection will be -5, or the opposite direction. So, all right, guys, so that'll be it for Transformations Part 1. Please be ready and waiting for Transformations Part 2 to come out very soon. And yeah, this has been eCoreAcademy e-learning platform. Please make sure to like and subscribe down below. Hit the post notification bell to get notified on any of our channel's latest posts. Visit our website at eCoreAcademy.org to get full unlocked access, as well as included videos on our YouTube channel, and to get full unlocked access on each and every one of our videos with integrated course quizzes, worksheets, and note sheets that go along with every single one, and they're all organized into course studies. And you can also make sure to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out to us. And please visit all of our socials at Facebook, Twitter, and Instagram. And please share our videos to anyone who might need it, or might find it useful or interesting. So that'll be it, guys. Hope you guys enjoyed. It's been AJ here, and I will see you guys in the next one. Peace.